Hello everyone and welcome to the channel. In this video, we'll continue taking a look at the demultiplexing circuit from the datasheet and specifically talk about how the data transfer works. I hope you enjoy. In the last video, we took a look at how the 65C816 multiplexes the bank address with the data pins, and we started building on the breadboard this circuit to latch the bank address. That was the first half of this circuit that's shown in the datasheet to manage the multiplexed bus. In this video, we'll take a look at the second half, which is the data bus buffer. Why do we need a buffer on the data bus? Well, it's about protecting us from bus contention. You see, the CPU is driving the bus when the clock is low in order to give us the bank address, and we need to make absolutely sure that none of our own devices is actually putting data on the bus when the clock is low. There's two ways of doing that. The first one is, well, to make sure that nothing is driving the bus when the clock is low. And we could certainly do that. I've seen designs that don't use any buffer and they work fine. You just have to be very careful. And the other option is to add a buffer to the pins and make sure that the buffer is never enabled when the clock is low. And so that's the safest option. It's not strictly necessary. And maybe we'll remove it in a future video in order to simplify the circuit once we're more confident in our bus management. But for now, let's build it. We'll start by taking a look at the datasheet for the 74AC245, which is the bus transceiver I'm going to use. The way this chip works is basically there are two ports, A and B. It transfers data from one side to the other. And you can change the direction of the transfer using the direction pin. So you can either go from A to B or from B to A. And you can also disable the buffer, meaning the outputs will go high impedance with the output enable. Let's add it to our KiCad project. So I have here our KiCad schematic. Let's start adding the buffer. Again, KiCad doesn't have the AC version I'm going to use, but that's fine, we'll add it later. So that's our multiplex data and bank address pins coming to the A port on the buffer and going out to the D port. So the direction is going from A to B when we are writing. So we want the data to flow through the device from A to B. And it's going to be from B to A when we're reading. And so for that, we can use the read-write signal from the CPU. If we take a look at the datasheet for the processor, we can see that the read-write signal is used to control whether the processor is reading or writing. When read-write is low, the data bus contains valid data which is written to the location. When the read-write is in high state, the microprocessor is reading data from memory. So what we want to do is to pass the read-write signal to the direction pin like this. But if you notice, we know that the read-write is going to be high when we're reading data, and we want data to flow from B to A. So our schematic is actually in the wrong order. We want to reverse port A and port B so that when we're reading data, it flows in the correct direction. So I'm going to make a copy of the symbol and change the order of the pins. So I'm just going to take all the pins and revert them so that it's easier to read on the schematic. And I'm also taking the opportunity to make this the AC version rather than the LS version. There we go. So now it's in the right order for a schematic. We can replace it here. There we go. So now when read-write is high, the data is going to flow from A to B, which means it's going to flow from the right to the left. And that's when we are reading, so this is correct. And when we are writing, the read-write is going to be low. And so data is going to flow from B to A, which is from the left to the right on the schematic. And so that's also correct. And lastly, we have the chip enabled signal. So this one is active low. And if we think about it, we want the buffer to be active when the clock is high, because that's when we are reading and writing to our devices. And so we need to use the inverted clock as a chip enable. And conveniently, we already have the signal because this is the same thing we're using for the latch chip. I want to do a bit of cleanup on the schematic because I think the buffer and the latch and the CPU could be a bit neater. So I'm going to reorder the pins on the CPU and invert the order of the latch and the buffer, and let's see how it goes. Okay, so this is our schematic updated. Let's take a look at how the buffer works in the timing diagram. This is the timing diagram where we left off in the previous video. First of all, I'm going to remove what's related to the latch because that's not what we're looking at today. And then the first pin I want to look at is the direction pin on the buffer. As we saw, the direction pin is hooked up to the read-write signal. We can see in the datasheet from Western Design Center that the read-write signal is treated the same as addresses. And so its timing is governed by the TAH and TADS timings, which we can see for CPU at 5 volts are a minimum of 10 nanosecond and a maximum of 30 nanosecond. So we can add that to the timing diagram. So this is the buffer direction pin. So it's hooked up to read-write, and we can see that the CPU will hold it for 10 nanoseconds after the falling edge of the clock, and it will be set up at least 30 nanoseconds after the falling edge of the clock for the next cycle. So how does that look like in terms of the output of the buffer? If we look at the datasheet for the 74AC245, in the switching characteristics at 5 volts, you can see that it's not actually specified the propagation delay from changing the direction pin to the output. So we have to assume a number here. And I'm going to take the worst case of all those numbers. So that's 1 to 10 nanoseconds. This worst case is also the propagation delay of the output enable pin. And we can see in the logic diagram that the output enable and the direction have very similar path in the chip. And so it should be a reasonable assumption to assume that they behave similarly. This is what it looks like. So if we assume that the propagation delay from a change in direction to the output being valid, we can see that the output is in the correct direction 11 nanoseconds after the falling edge of the clock. And for the next cycle, it takes 40 nanoseconds for the direction to be valid. So if I overlay on the diagram the times where the direction is valid, you can see that on both a read and a write cycle, the direction of the buffer is going to be correct during the whole write and the whole read. So we're pretty good on timing with the direction pin. The next pin I want to look at is output enable. We can see that output enable is hooked up to the inverted clock. So that's exactly the same signal we already talked about in the previous video for the latch. We know that there is this undefined period of between 1 and 7.5 nanoseconds after each clock edge. If we take a look at the datasheet for the buffer again, we can see that the propagation delay of the buffer turning on, which is the TPZH or PZL. So that's from high impedance to high or high impedance to low. So the buffer is turning on, is at worst 1 to 9.5 nanoseconds. And the buffer turning off, so that's the third line here, is 1 to 10 nanoseconds. So if you add that to the timing diagram, this is what it looks like. We see that the way it's hooked up, the buffer turns off at a minimum of 2 nanoseconds after the falling edge of the clock, and it could take up to 17.5 nanoseconds for it to turn off. Then it's off for a while, and when the clock is rising, there's again 2 nanoseconds minimum and a little bit less, so that's 16 nanoseconds for it to turn on. And finally, we want to look at the outputs and see in a read and a write cycle what the new timings are related to the data pins outside of the buffer. We can see here that the propagation delay from input to output is 1 to 7 nanoseconds. If we take a look at a read cycle, for example, we know that the CPU wants the data to be held 10 nanoseconds after the falling edge of the clock. But we also know that there's a 1 nanosecond propagation time from the buffer input to the buffer output. And so basically what that says is we need to hold the data at the buffer input for 9 nanoseconds after the falling edge of the clock. And we know that the CPU has a data setup time of 10 nanoseconds, but the worst propagation delay of the buffer is 7 nanoseconds. And so we need to present the data at the inputs of the buffer at least 17 nanoseconds before the falling edge of the clock. In a write cycle, we know that the CPU is holding the data at least 10 nanoseconds after the falling edge of the clock, and we have a 1 nanosecond propagation delay. So we see the data that is written at the output of the buffer at least 11 nanoseconds after the falling edge of the clock. We also know on the other side that after the rising edge of the clock, the write data starts appearing on the CPU pins at least 30 nanoseconds after the rising edge of the clock. And so if we add to that the worst case of 7 nanoseconds of propagation, we know that the write data is available after 37 nanoseconds after the rising edge of the clock. These are all the outputs of the buffer characterized. If you notice, there's kind of a timing issue here. If I overlay on the timing diagram the times when the buffer is off and on in red and green, you can see that the buffer is not actually on when we're trying to read or write data. And the buffer is not actually off when we want it to be, which is when the CPU is driving the bank address. So what we would ideally want is to shift those intervals to the right so that we are sure that the buffer is off when the CPU is driving the bank address. And we are also sure that there's enough time for the CPU to read or to write data. So ideally, from the falling edge of the clock, we would shift it to at least 11 nanoseconds after the falling edge of the clock so we don't lose any data here. So for that, we need to delay the output enable signal. However, there are some modifications I want to make to the logic of the circuit in the next 2 videos. And so I'm going to ignore this problem for now, and we can go back to it once the logic of the circuit is completely done. So for now, let's just hook up the buffer on the breadboard and see how it looks like. Okay, so now we have all the address pins decoded, and we actually need the data pins here. So for this, the datasheet recommends using a 74245, which is the chip that I have here. And on this chip, we can actually select the direction that we want it to go, so we can actually put it the right way around. So it needs power and ground. And then we need to transfer the data pins over. So that's all the data pins. And then we need the direction pin. So direction pin is going to say whether we transfer from the top to the bottom, from the bottom to the top. So we want to transfer from the top to the bottom when the CPU is writing, so when the read-write line is low. And we want to transfer from the bottom to the top when the CPU wants to read, so when the read-write line is high. So we can just tie the read-write line directly to the direction pin. So the read-write line is here. And then the only remaining pin is the output enable. And we want this device to be enabled only on the second half of the clock cycle, because that's the only place where the data is valid. So we need to tie output enable to the inverted clock. Getting a bit tight here. Okay, so this should be everything. I'm only missing a coupling cap on the bus transceiver chip. And there you have it. All the data pins are now available here. The bank address is available here. The normal address is over here, and then all the control lines are done at the bottom here. So there are actually two improvements that I've thought about doing to the datasheet circuit. The first one is, since we're only activating the bus transceiver on the second half of the clock cycle, its outputs are going to be floating during the first part of the clock cycle. And since all our circuit is going to be CMOS chips, we really don't want any floating pins. So I'm going to add pull-down resistors to all of the outputs from the transceiver. This is a 1K resistor array, and we can pretty conveniently plug it here to have all the outputs pulled down through the ground pin here. So that when the chip is not driving the outputs on the first half of the clock cycle, they're going to be pulled down to 0 by this resistor. The second improvement I've thought about doing to the circuit is a bit more complex, and it resolves around the bus enable pin of the CPU. And that's going to be the subject of our next video. So I hope you enjoyed this one. Let me know in the comments if you've got any questions or feedback, and I hope to see you in the next one. Bye.